Hey there everyone, my name is Jacob Clark and today we will be talking about covalent adaptable networks, or CANs for short, and their potential use for recycling of thermosets. So the world we live in today is only made possible through the substantial increase in materials available to use. Unfortunately, many of these materials are largely single-use or non-renewable in nature. This has led recent movements to focus largely on sustainability. To counteract the adverse effects of production, recycling systems have been put in place to extend the life cycle of these materials. One such material class is plastics, or more scientifically known as polymers. Polymers are materials made of large repeating chains of molecules. Some polymers, such as thermoplastics, are currently recycled, whereas other polymers, such as thermosets, aren't currently being recycled. To understand why some plastics are recycled and others aren't, we first have to dive into the difference between thermoplastics and thermosets. Thermosets and thermoplastics are two different polymeric materials that differ in their properties, processing, and application. Thermoplastics are polymers that can be melted and remolded multiple times without undergoing significant degradation. They have a linear or branched molecular structure and are held together by weak intermolecular forces. This allows them to be melted and reshaped using various processes such as injection molding, extrusion, and 3D printing. Common household examples of thermoplastics include Legos, which are made of acrylonitrile butadiene styrene, or ABS for short, or plastic containers, which are usually made of polyethylene terephthalate, or PET for short. Thermoplastics have the advantage of being easy to process and recycle, making them the natural choice for packaging, automotive, and consumer products. On the other hand, thermosets are polymers that undergo chemical reaction when they are cured or hardened, resulting in a rigid, highly cross-linked structure. Though this results in a stronger material, thermosets unfortunately cannot be melted or remolded. Common examples of thermosets include polyurethane foams, such as the one in your mattress topper or in your car seats, epoxies, and polyester resins. Thermosets are also known for their excellent heat and chemical resistance, making them amiable for high temperature and harsh environments. They are often used in aerospace, automotive, and electronic industries where durability and strength is critical. Though thermoplastics and thermosets are both useful, sometimes we want a material that can be recycled and also maintains high mechanical strength. In cases such as these, we turn to covalent adaptable networks. So what are covalent adaptable networks, or CANs? CANs are a class of material that can change their chemical structure or properties when an external stimulus, such as heat, light, or pH, is applied. They have been touted as a way to bridge the divide between thermoplastics' superior reprocessability and recyclability and thermosets' high mechanical strength and durability. CANs are made possible through dynamic covalent bonds, which are reversible bonds at elevated temperatures, but stable bonds at ambient temperatures. Thus, thermosets can achieve macroscopic flow and stress relaxation, which was previously thought to be impossible. When a stimulus is applied, the network will be able to undergo viscoelastic solid to viscoelastic liquid transitions. This allows the network to adapt to changing environmental conditions, self-heal, or even be recycled. So now that we know what CANs are, let's see how they can be classified. CANs can be classified into two different groups, associative and dissociative bond exchanges. Dissociative CANs are where a complete bond rupture occurs upon heating, and then the bond subsequently reforms upon cooling. This reversible cleavage of bonds within the network leads to a decreased cross-link density. Associative CANs, on the other hand, are networks which bonds are only broken when new ones are formed. This bond-forming bond-breaking sequence occurs without a change in cross-link density or a decrease in connectivity. Another term used synonymously with covalent adaptable networks is Vitrimers. Vitrimers are a subcategory of CANs that must be covalently bound by a network of chains. They must have a network topology that can be altered by associative exchange reactions, which allows for thermal processability. Associative exchange in Vitrimers is triggered by heat and leads to a linear dependence of viscosity with inverse temperature. A lowered viscosity caused by dynamic bond exchange is what triggers stress relaxation and network rearrangement in these materials. Below the topology freezing temperature, TV, Vitrimers act as thermosets, whereas above the TV, Vitrimers flow with an Arrhenius trend, being viscoelastic, reprocessable, and reshapeable. Though the glass transition temperature and topology freezing temperature seem similar, TG is characterized by the reptation of carbon chains causing a transition from brittle to ductile. TV, however, is the threshold above which dynamic molecular rearrangement through exchange reaction becomes significant. When TG is lower than TV, both glassy and rubbery states are identified. However, when TG is greater than TV, a glassy state is present until bond exchange becomes dominant and the Vitrimer behaves like a viscoelastic fluid. As stated before, covalent adaptable networks are made possible with the implementation of a catalyst. The catalyst is crucial in enabling the reversible exchange of covalent bonds within a material. The catalyst can also control the rate and selectivity of the bond exchange reaction, leading to a more efficient and controlled adaptation of the can. Choosing a catalyst for the can is highly dependent on several factors, including the type of dynamic covalent bond in the material, the desired reaction condition, and the specific properties that are needed for the application. The catalyst can also lower the activation energy of the bond exchange reaction, allowing the reaction to occur at lower temperatures than would be possible without it. There are 5 general considerations you want to keep in mind when choosing a catalyst for a can. The first is that the catalyst should catalyze the selected bond exchange reaction and avoid any unwanted side reactions leading to degradation in the material. Number 2 is that the catalyst should have a high activity, allowing the bond exchange reaction to occur at reasonable rates under mild conditions. Number 3 is that the catalyst should remain stable under normal reaction conditions, not degrading or deactivating at any time. The fourth consideration is the cost of catalyst, which should be heavily considered, especially if large-scale production is intended. Finally, the catalyst should be compatible with any other areas of the can, including the polymer backbone and any additives. Many different types of catalysts can be used for cans, but the typical choices are transition metal catalysts, organocatalysts, and enzyme catalysts. Now that we have gone over exactly what covalent adaptable networks are and how they work, let's look into how thermoplastics and thermosets are currently recycled. Thermoplastics are recycled based on their identification number 1 through 7, typically located at the bottom of the bottle or container. Here are the common designations for all the polymers. The actual sorting method for the plastic is highly dependent on the size of the recycling plant and the budget. Smaller facilities usually use manual sorting, which involves the worker physically sorting through the materials and identifying them by type, color, or other physical characteristics. Larger facilities usually automate sorting through machines such as near-infrared sorters or optical scanners. NIR uses wavelength signature to distinguish the differences between each polymer. It does not use color. Optical sorters, on the other hand, use cameras and sensors to determine the polymer based on their color and transparency. It does not distinguish plastics based on resin composition. These technologies help reduce the amount of plastics that end up at landfills or in the environment while still lowering greenhouse gases and conserving natural resources. Thermosets, on the other hand, have a lackluster end of life cycle. Since thermosets are cross-linked and therefore cannot be remelted, they usually end up being incinerated or disposed of in landfills. Thus, development of covalent adaptable networks for industrial scaling can help drastically improve the recyclability of thermosets. Though covalent adaptable networks have been successfully implemented into many different systems, the 3 we are focusing on today are carbon fiber reinforced epoxy resins, polyurethane foams, and imine bonds. One such way covalent adaptable networks were investigated for recycling was in an epoxy-based carbon fiber composite. In this paper, you and associates were able to fully dissolve the epoxy resin in ethylene glycol at 160 to 180 degrees Celsius. The associative can was recycled via transesterification. The result of this study was clean carbon fibers with nearly 100% recyclability and mechanical strength, and an epoxy that was able to repolymerize. This ultimately leads to a sustainable way to recycle carbon fibers, which is a highly expensive material. Another study by Ellison and Associates looked into using covalent adaptable networks in polyurethane foams. This study first took methylene diphenyl diisocyanate and a commercially available polyester polyol and synthesized a polyurethane foam using both physically blown and chemically blown agents. The foam was synthesized with a small amount, roughly 0.35 mole% of dibutyl tin dilaurate, or DBTDL, which was the catalyst. Both the PU foams and films exhibited stress relaxation at elevated temperatures using the dynamic carbamate exchange reactions. The PU foams were reprocessed using twin screw extrusion to remove the gaseous filler. The remaining polyurethane could be used to produce filaments or films that could be retested for stress relaxation. These findings should hopefully enable the bulk reprocessing of commercial polyurethane waste. The third system we are looking into for recycling are imine bonds, or C double bond N bonds. Imine bonds, commonly called Schiff-based, are often used for polymeric assemblies. This is primarily because imine dynamic bond exchange reactions occur under relatively mild conditions. Zhao and Associates created a Schiff-based epoxy resin by embedding imine bonds into epoxy cross-link networks as intermolecular linkages. The resultant epoxy thermoset possesses good reprocessability and comparable properties to conventional high-performance thermosets. By acid-acid hydrolysis of the imine linkages, reshaping and repairing of the thermoset are realized. After drying at 120 Celsius for 24 hours, the sample has a stress of roughly 42 megapascals and a strain of 4.1%. These properties of the fully dried sample with reformed imine bonds are comparable to the original sample. There has been a significant push towards recycling and sustainability in recent years, driven by growing awareness of environmental impact of human activities. Governments, businesses, and individuals around the world are taking steps to reduce waste, conserve resources, and minimize their carbon footprint. While there is still much work to be done, the increasing focus on sustainability and recycling through the use of cans is a positive step forward for our future and planet. Though research on covalent adaptable networks has drastically increased over the past few years, much work still needs to be done on implementing this technology commercially. This, in conjunction with increased public awareness of recyclable material and subsequent prioritization of these efforts, can lead to a lasting impact on the sustainability and longevity of our society. Thanks for watching. If you enjoyed this video, make sure to like, subscribe, and comment with future video ideas. Peace.